I'm ready, I think.
Good evening, and welcome to our, it seems to be probably our final presentation, public presentation for the CLG. We have a special guest this evening. It's Dr. Gordon Edwards from Montreal, and Dr. Edwards has been involved in the nuclear issue for a long time, and since 1975 he's been with the Canadian Coalition for Nuclear Responsibility. And he has given us some pamphlets and some booklets here for your information. We will photocopy them for you if you want. Not tonight, of course, but in the future, there's a few other ones as well. And you're welcome to come up and inquire about them, and we'll do what we can to photocopy them and get them out to you as soon as possible. As I mentioned, this might be our last public meeting. We're going to talk about opting out of this process. There seems to be a strong public opposition to having Atikokan continue to look at the possibility of cutting low-level radioactive waste in our community. And from that, there's a petition going around, and we've been conducting a telephone poll, and it seems to be very strong in opting out of this process. So, to not talk anymore, I'm going to pass it on to Dr. Edwards.
Thanks very much. Well, good evening. Nice to be back here. Although I wish I were back here under under different circumstances, maybe just taking a canoe trip in Quetico. My cousin, Peter Grew, was parish priest here for a while. Some of you might remember him. And also my sister taught here for a while, Joan Sagan. That was many years ago in the elementary school. And of course, I've been here before, back in 1978 when Atomic Energy of Canada Limited was poking around, looking for a hole in the ground. And here we are again. And what I'd like to do this evening is to try and be of assistance to you in understanding a little bit of the history and nature of these particular wastes, and also how it fits into the general overall context of the nuclear situation and nuclear waste generally. I just might mention that everyone describes these wastes as low-level radioactive wastes, and it kind of begs the question, well, what's high level if this is low level? Basically, the difference is that when you put uranium fuel into a nuclear reactor, something very bizarre happens. The uranium atoms get literally split, and the result is they don't disappear. You get all these hundreds of different what are called fission fragments. These are actually fragments of uranium atoms which have been split in the reactor. Same thing happens in an atomic bomb, only it happens very suddenly and violently, and the fission products are scattered all over hell's half acre and comes down as radioactive fallout. In a nuclear reactor, the same thing happens more slowly, in a more controlled way, and the fission products are contained in the fuel instead of being scattered into the environment. But they're extremely dangerous. And in fact, they're millions of times more radioactive than the uranium that went into the fuel. And this stuff is high-level radioactive waste. And if we just had one of those bundles here, a bundle is typically about this big and weighs about 58 pounds, and if I had one of these bundles here, well, if it was just a fresh bundle before it had gone into the reactor, I could have it here all evening while I'm talking, and nobody would particularly get a large dose of radiation. Probably might want to put it under the table perhaps, but it's not going to give anybody a lethal dose of radiation. It's not going to kill anybody, although it could slowly increase their chance of getting cancer many, many years later. On the other hand, if that same fuel bundle had just come out of the nuclear reactor after being in there for a couple of years, it would kill me and most of you just in a short period of time. As a matter of fact, if you were 1 meter away, just 1 meter away from one of these spent fuel bundles or used fuel bundles for only 20 seconds, you would get over 1,000 rads of radiation, which will kill any human being. That means that if you were exposed for 20 seconds at a distance of 1 meter, you'd be a dead person, although you might not actually keel over for a couple of days. Well, you would keel over, I guess, quicker than that, but you wouldn't actually expire until a couple of days later. That is high-level radioactive waste. And that's what everybody talks about when they talk about high-level radioactive waste. The difference with low-level radioactive waste is that you do not feel any immediate health effects just by being close to it. It's not going to cause any immediate health problems simply because it's nearby. That's the difference. It doesn't mean that it's not radioactive, and in fact it doesn't mean that it isn't very radioactive. It is quite radioactive, but it's radioactive in a different way. And I'll try and explain what I mean by that in the course of this presentation. I'd like to show you a few transparencies, if I may. Where's the doohickey? Right here? Oh yeah, okay. This is simply an illustration of what we call the nuclear fuel chain. Well, sometimes they call it the nuclear fuel cycle, but the most remarkable thing about it is that it's not a cycle. It's a chain that leads to nuclear waste. What happens is you mine the uranium out of the ground, you mill it. That's usually done at the same site as the mine. Then you send it to a refinery. That's in Port Hope, Ontario. That's where the refinery is. And this is a chemical processing plant, basically, that refines the uranium and puts it into a different chemical form. Now, that's basically what we're talking about when we talk about Northern Ontario at the present time. When we talk about Elliott Lake, we're talking about mining and milling. When we talk about waste from Port Hope, we're talking about refinery waste. So we're talking about what's called the front end of the nuclear fuel cycle, or the nuclear fuel chain. Now, once the fuel is fabricated, once the uranium is fabricated into fuel, and sometimes for some reactors it has to be enriched to do that. For our reactors, we don't need enrichment. We can just use the actual natural uranium and fabricate it into fuel. It then goes into the nuclear reactor, and then it produces this spent fuel, which I just described to you, which is the high-level radioactive waste. Now, don't be surprised if the same people who are currently getting communities to consider low-level waste might not be back in a few years knocking on your door and saying, hey, by the way, we've got some high-level waste too. Wouldn't you like to consider the possibility of perhaps accepting the high-level waste? And that would be essentially the spent fuel, or what happens to the spent fuel when it's processed. Now, one thing that they like to do with spent fuel in various countries is reprocessing. Reprocessing the spent fuel is a difficult, dangerous operation. The reason it's difficult and dangerous is because of the intense radioactivity of the spent fuel, which I described to you. It means that it cannot be handled by human hands at that point. So that once it comes out of the reactor, it has to be all done by robotic equipment. And what they do is they have a robotic chemical plant which reprocesses the spent fuel, and what that means is dissolving it in nitric acid and separating out one particular constituent of the spent fuel, which is called plutonium. And that plutonium is usable either as more fuel for the reactor, or if you wanted to make a bomb, you could make a bomb from plutonium as well. Anything that can be used as fuel for a reactor can, if suitably handled or transformed, could also be used for a nuclear explosive eventually. And plutonium, in fact, could be used either way. It could be used for bombs, it could be used for nuclear fuel. That's why I have this arrow going back up to fuel fabrication again. And what's left over from that, either the reprocessing or the unreprocessed spent fuel, that's what we call high-level waste. Okay? Now, the high-level waste is specifically characterized by the fact that it's extremely toxic. In fact, a spent fuel bundle is probably the most toxic thing we have on the face of the earth. When you take a look at this is a rather poor Xerox or graph taken from the 1978 publication called A Race Against Time, which was the Ontario Royal Commission on Electric Power Planning that looked into nuclear power and so on in the context of electricity needs for Ontario. And what this graph is supposed to represent is how toxic, the ingestion toxicity, that means how toxic this is if it happened to get into the water or into the food, as a function of time. On the bottom we have time, and up this way we have toxicity. And the scale on the bottom starts at 1 year after being out of the nuclear reactor and goes up to this end, which is 10 million years after being out of the reactor. And what this chart shows is what happens to the toxicity over 10 million years when it comes out of the reactor. And basically, it starts off very toxic, and with time, it diminishes because of radioactive decay, and it diminishes down to, after about 50,000 years, it hits a sort of a low point, and then it actually becomes more toxic again, a little bit more toxic, because of changes that are going on in the spent fuel. But it stays well below that toxicity level, which is the case for the first 1,000 years. The first 1,000 years is the most dangerous. After that, it is still dangerous, however. Now, it turns out that the U.S. Geological Survey, which is well, we have the Canadian Geological Survey, the U.S. have the U.S. Geological Survey. It's a government agency of geologists who advise them on geological matters. In 1978, they published a very interesting booklet on high-level wastes, and they pointed out a couple of interesting things. The first thing they pointed out was that if you took the spent fuel from the nuclear reactors that are now operating in the United States, if you took the spent fuel at the year 2000 and asked the question, how much water would you need to dissolve those wastes to what are called maximum permissible levels of contamination? In other words, there's only a maximum amount at which you were permitted to contaminate drinking water before it becomes unacceptable, according to whatever acceptable is, okay? I wouldn't personally consider it very acceptable to have water contaminated to the maximum permissible amount. But nevertheless, how much water would it require to dilute these wastes to what are called the maximum permissible levels? And the answer they come up with is quite staggering. They said if you took all the fresh water in the entire world, from all the lakes, all the glaciers, all the rivers, even the soil moisture and the groundwater under the ground, all over the world, and added it up and doubled it, that would be about how much you'd need to dissolve it to maximum permissible levels of pollution. Now, they also pointed out that even after 1 million years, which is here, even after 1 million years, the amount of water required to dilute these wastes to acceptable levels would be comparable to what's in the Great Lakes system. So you're still talking about a huge amount of water. And of course, the point they're making is not that this is going to happen, but that this is why you can't allow even 1% of this stuff, or even 0.1%, or even 0.01% of this stuff to get out into the environment. You've got to contain it basically perfectly, basically forever, if you want to be responsible about it. Now, the other thing that is pointed out in the report is that uranium mill tailings, these are the tailings which are left over from the front end of the fuel cycle before you put the uranium into the reactor. Going back to Northern Ontario, we're talking about the stuff that's at Elliott Lake in the mine tailings there. These mine tailings are a lot less toxic than the high-level waste when the high-level waste comes out of the reactor, but after about 1,000 years or two, or actually this is more like, well, after about 1,000 years, the difference in toxicity is not nearly as great. In fact, the tailings are not as toxic as the high-level waste, but they're getting there. And in fact, once you get past a certain point, the tailings are just as toxic as the high-level waste. And that's the point I would like to make to you, is that these so-called low-level wastes are very toxic. And that if you wait, and by the way, on what basis do they make this comparison? How do you compare mine tailings with high-level waste? Well, the way they compare them is they say, let's take the fuel for a reactor for 1 year, for example, and look at the high-level waste that comes out of the reactor, and compare that with the low-level waste that's generated before the fuel goes into the reactor, and that's what you compare. In other words, you compare the amount of waste before it goes into the reactor with the amount of waste that comes out of the reactor for the same reactor. And you come up with the fact that after a few thousand years, they're about equal in toxicity, and it's nothing to laugh at. It's considerable. Now, another thing I'd like to, a remark I'd like to make is that radiation is perhaps not the best word to use. In fact, I prefer to use the word radioactivity, because radioactivity has one meaning, whereas radiation has many meanings. When we talk about radiation, we could be talking about microwave radiation, we could be talking about television waves, radio waves, we could be talking about sunlight. But when we talk about radioactivity, we're talking about radioactive material. We're talking about material, actual physical material, which is somehow different, radioactive. And this material, like all materials, It's just like a chemical pollutant, except its main claim to fame is not the chemistry, but the radioactivity. And the way it gets into our bodies is the same way any pollutant would get into our bodies, through our food, through our water, through our breathing. If you're breathing contaminated air or eating contaminated food or drinking contaminated water, that's how you get contamination. And there's no difference in that respect between radioactive substances and non-radioactive substances. What happens with radioactive substances is that they are also not different from other substances in the sense of where they go in the body. Radioactive substances in your food, if you had radioactive iodine in your table salt instead of normal iodine, every table salt, you know, has iodine. And why is iodine added to the table salt? Well, it's one of the few cases we have of preventative medicine. Iodine is added to the table salt to prevent goiter, because iodine, in fact, goes to the thyroid gland in the neck, and it acts as a preventative for a disease called goiter, which used to be fairly common at one point. And as a result, we don't see much goiter. Well, if you had radioactive iodine in the salt, it would also go to the thyroid gland, because chemically, it's exactly the same as non-radioactive iodine. I will explain what the radioactivity means shortly. I'm sure you've heard it before, but perhaps you'll bear with me when I go over it again. So that what happens is different types of substances go to different parts of the body. Radon-222, which would be one of the substances associated with the waste from Port Hope, for example, radon-222 is a radioactive gas which you breathe and it goes into your lungs and can cause damage to the lungs. Uranium goes to the lungs and to the bone. Plutonium goes to the lungs and to the bone. Here is something called polonium. Now, polonium is also present in the waste from Port Hope. That would be one of the important constituents in the waste from Port Hope. And polonium goes to the spleen as well as to other organs in the body and can cause damage there. Radium, which is an important constituent of the waste. Radium behaves a lot like calcium. And calcium, you know, is necessary for good strong bones and teeth. Well, that's where the radium goes too. The body, when it gets radium in the diet, thinks it's calcium. And so the body busily digests it and puts it away in the bones and the teeth and the milk, which is where it would have put calcium normally. And of course, we do have radium in nature, but small quantities of it. If you get more radium, usually radium is present in very small, minute amounts in nature, and if you get an increased diet of it, the body doesn't know that you're getting an increased amount. It thinks you're getting an increased calcium and just puts it where it thinks the calcium should go. And that's why radium is particularly dangerous as a possible damage that it can do to the bone marrow or to the bones or to the jaw or to any part of the skeleton, really, and so on. Now, well, if this is all the same, then what is different about radioactivity? And for this, I'd like to just go over some of the things which I went over at the school today with some of the students there. And it's just the history of how we found out about all this. It turns out that back around 1896, I'm not sure of the precise year, I should have looked it up before I came, but 1896 or 1897, radioactivity was discovered. It was always around, but it was discovered. And it was discovered by a Frenchman named Henri Becquerel, who was interested in different kinds of substances that glow in the dark. And of course, you know, a lot of different things glow in the dark, and generally if you leave them in the dark long enough, they lose their glow, and you got to put them back out in the sunlight to get charged up again. Then you put them in the dark and they glow again, and it's always fascinating. And this is something he was interested in. And one of the rocks he had, which glowed in the dark, was particularly interesting, but he put it in a drawer and left it there for several weeks. And of course, it should have lost its glow completely. Well, a little later on, he reached into the same drawer and put a photographic plate in there and left it there for a while and put the rock on top of it. Then later, he took that photographic plate and developed it, and he discovered, much to his amazement, a kind of an explosion of light on the negative of the film, which was right where the rock had been. And he couldn't understand it at all, nor could any of his scientific colleagues, because how on the earth can a dead rock be giving off energy or light without any external energy supply? And this was the invention of this was the discovery, rather, of radioactivity. He also carried one of these rocks in his pocket and got a very nasty burn that wouldn't heal. Unlike most burns, which sort of heal after a little while, this one just kept hanging on and wouldn't heal. And that was a radiation burn. And people very quickly learned that if you're going to play with this stuff, you've got to be careful because you can get burnt. And those burns are not like normal burns. They last a lot longer, and they're very difficult to heal. And so people learned to handle this stuff with respect from a very early time. Now, the question was, another thing, by the way, Madame Curie, Marie Curie, who was working in Paris, originally from Poland, was working in Paris, and she was the one who actually isolated the first radioactive substances and identified them. And those first two substances were polonium, which she named after her native Poland, and radium, which she named after the radiating pattern of lines that were on that photograph of Becquerel's. And these two substances are two of the principal substances you will find in the waste from Port Hope, radium and polonium. Actually, there was a movie that ran on TV Ontario not too long ago, which was the story of Marie Curie. And it showed her great efforts to take all these rocks, which, by the way, came from Czechoslovakia. She went and bought tons of these rocks that Becquerel had got from Czechoslovakia and brought them to her laboratory in Paris and worked away crushing up these rocks and diluting them with acid, dissolving them, and doing chemical. And what she did was she kept separating out finer and finer portions of this solution, always following where the radioactivity went. And the part that wasn't radioactive she was not interested in. She kept concentrating on the part that was radioactive and purifying it and refining it. And she finally got to the point where she went in and she looked, and all she had was an empty beaker. There was nothing in it. And she thought, what have I done? All this work for nothing. There's nothing there. And she went home, and then she came back in the middle of the night, and she opened the laboratory door, and there was this beaker glowing very brightly all by itself in the room. And she realized that the beaker was not empty, that there was something there, and that was radium. She had discovered radium, and which glows quite brightly when it's in its concentrated form. So people started wondering, well, what can we do with this wonderful toy? And they thought of a few things, some of them really, really crazy. People did some really crazy things with radium. And one thing they did was they used to sell bottled radium water. People would drink radium water because they figured, well, if it's energetic, it'll probably pep you up. So maybe it'd be a good tonic. And a lot of people drank a lot of radium water, much to their regret later on. But the two principal uses they come up with was, one was, especially in the First World War, they thought it'd be great for fighting wars at night to have dials and watches and things that you could read at night. So they painted them with radium paint. And for this purpose, they hired thousands of young teenage girls to work in these painting factories to paint the radium dials. And after the war, this thing caught on as a kind of a fad, and they just painted dials just for the heck of it, so that you could have an alarm clock that glowed in the dark all the time, whether it had ever been in the sunlight or not. And these women, there were about 4,000 in the United States who worked in these radium dial painting factories, and there were many thousands more in European factories. And they were always young women. It always seemed to be teenagers or early 20s. And these women, by about the late 1920s, some dentists started reporting in their own journals, and it became common knowledge, there were newspaper articles about it and so on, of a phenomenon called radium jaw. These girls were developing strange jaws, which the dentists would notice that their teeth were coming out because the bone was actually dying and receding. And and also in some cases it was getting very porous. The bone was getting very porous, in some cases brittle, and in some cases it was actually getting deformed. There were deformations in the skeletal formation of the jaw. And everybody was saying, what's going on? Well, it must have something to do with the radium painting because they're all girls who work in the radium painting factory. And then by the 30s, it became apparent that this was not the worst of it, that there were a lot of these girls were dying of bone cancer and leukemia, and also of various types of head cancers, cancers of the sinuses, and cancers of the mastoid cells, and in some cases cancers of the palate, which is the roof of the mouth, and brain cancers. And This was documented best in 1936. There was a major article written by a medical doctor called Martland, who wrote a report. I forget the exact title. I should have written that down too. But it has to do with basically illnesses in radioactive persons. I know radioactive persons was part of the title. And what he was referring to was the dial painters principally. And he documented very clearly that this was an incredible increase in cancer of the bone, which is a very rare form of cancer. And so you really notice it when you get a sharp increase in it. And also these other types of cancers, and that it must be due to the radium. And he made the point that, and this is almost a direct quote, he said, alpha particles appear to be the most dangerous and destructive agents known to science. And what he was referring to was the alpha radiation that is given off by radium. Now, it turns out that radioactive substances, what are they? Well, they are substances whose atoms are unstable. And these unstable atoms, most atoms are stable. You see, like if you have water, it's made up of hydrogen and oxygen atoms. And those hydrogen and oxygen atoms, according to our knowledge of science, those hydrogen and oxygen atoms have been around forever. The same hydrogen and oxygen atoms might have been in the flesh of a dinosaur millions of years ago. But those hydrogen and oxygen atoms haven't changed. They've simply recombined in different ways. They stay the same. But what Marie Curie had discovered, and Becquerel and the rest, was that some atoms do not stay the same. They change. And that's what happens with radioactivity. The atom literally undergoes a kind of a microscopic explosion. And when it explodes, it is no longer radium. It changes into something else. And I'll tell you what that is in a moment. And when it explodes, it gives off little pieces of itself. And these are actually chunks of material. It's not just invisible rays. They're actually chunks of material. And some of the chunks are small, and that's called beta particles. And some of the chunks are large, and those are called alpha particles. The alpha particles are about 7,000 times larger than the beta particles. That's there's an exact ratio in the size. And these alpha particles, because they're so large, they don't penetrate very far into tissue. In fact, they go only a very short distance. In fact, an alpha particle will only go about the same distance as the width of a hair follicle. You know, the hair grows out of these little pores, special pores called follicles, and the diameter of a typical hair follicle would be about 50 microns or less. And an alpha particle will travel about 70 microns in soft tissue. And what that means is that alpha radiation is very little penetrating power, but because it's so massive, it does a great deal more damage than beta radiation. In fact, alpha radiation is considered to be, by the authorities, about 20 times as damaging as the corresponding dose of beta radiation, and about 20 times as damaging as the equivalent dose of gamma radiation or X-rays. Alpha radiation is dose for dose the most damaging form of radiation. But because it has such little penetrating power, it is not an external hazard. Outside the body, it's not going to hurt you, because it can't penetrate. Even through your skin, it can't penetrate to get at the living cells underneath. And so the alpha